In our last video, we just looked at how chlorine loves to make bonds with sodium because sodium wants to get rid of its last electron, so it tends to give away an electron, and chlorine loves to accept electrons. So when sodium bonds with chlorine, what they do is sodium gives chlorine an electron, making sodium positively charged because it now has one electron less, but the same number of protons. And then chlorine gains an electron. So sodium and chlorine love to bond, but forming what is called an ionic bond because one becomes positively charged and the other negatively charged. The positively charged atom is known as a cation. The negatively charged atom becomes known as an anion. Okay, and this is an ionic bond. You should know what sodium chloride is, sodium plus chlorine, or sodium chloride. This is more commonly known as table salt. Yummy, it's table salt. We all love to add salt to things, into our food, and make it flavorful. And that's because sodium and chloride bond so much that the ocean is full of sodium chloride bonds. Okay, so again, when you have an ionic bond, you're going to form an anion and a cation. One atom becomes positively charged, the other one becomes negatively charged. This is your ionic bond. Sodium and chlorine do this to form table salt. Another type of bond that is formed is what is called a covalent bond. And there are two types of covalent bonds, nonpolar covalent and polar covalent. So let's look at both of these so we can get an idea of what is happening here with the polar covalent and the covalent bonds. So let's get a whiteboard here. I'm going to let's use carbon as an example, since we were talking about carbon before. Carbon, if you remember, is atomic number 6, atomic weight 12, which means again that it's going to have 6 protons. It's going to have 6 neutrons because 6 plus 6 is 12, and it has 6 electrons because it is a neutrally charged atom. So if we were to draw carbon, we would put 6 positives and 6 neutrons in the nucleus, and then the first orbit going around is going to have 2 electrons. The next orbit going around would have 4 electrons. Why? Because 2 plus 4 equals 6, and we have a total of 6 electrons. Oops, that came out bad. I have a total of 6 electrons. As you know, the last orbit wants to be full with 8 because of the octet rule. Because you only have 4 left in this valence shell, you only have 4 electrons, then what you're going to want to do is obtain 8 electrons. So carbon loves to bond with many other types of elements. Actually, carbon has a habit of forming bonds with up to 4 different elements because it needs 4. So for instance, carbon can bond with 4 hydrogen atoms because that would give it hydrogen would share its 1 with carbon to make it have all of them. Hydrogen is not going to give away its electron because hydrogen is only missing 1 electron to be full. So hydrogen tends to form shared bond. So when carbon bonds with 4 hydrogens, again, that will look like carbon with hydrogen, with hydrogen, with hydrogen, and with hydrogen, it forms an equal bond. This is not an ionic bond because hydrogen doesn't give away an electron. Carbon doesn't give away an electron either. Instead, they all just share electrons, so nobody becomes neither positively nor negatively charged. This is called a non-polar covalent bond. So when you're thinking about polar, I always say think about the poles, South Pole, North Pole. They're on opposite ends. So when you have a polar covalent bond, one is going to be slightly negative, one's going to be slightly positive. In a non-polar covalent bond, nobody is positive or negative. Instead, they equally share electrons. Equally share. Another example of this would be carbon with carbon. Because carbon is missing 4 to be complete, then carbon can bond with carbon because 4 plus 4 would give you the 8. And so then what they end up doing is their last shell, they would share it to have a total of 8 electrons around it. Again, this is called nonpolar covalent bonds. This is different from your polar covalent bonds. So let's look at what a polar covalent bond is. This guy's going to be a little bit different. So here you're not going to have equal sharing at all. But it's not going to be so unequal that it forms ionic bond. So let me think of a good example here. Oh, of course, water. Water is a perfect example of that. Let's look at the atom of oxygen for a moment, okay? So oxygen, one moment here. Okay, oxygen is atomic number 8. Sorry, atomic number 8. And atomic weight for oxygen is 16. So atomic weight of 16. So you should know by now that that means that oxygen has 8 protons. It's going to have 8 neutrons because 8 plus 8 equals 16. And its number of electrons are the same as the number of protons because it is not positively nor negatively charged. So it has 8 electrons. So if we were to draw oxygen, you'd put protons 8, neutrons 8. The first orbit, this is protons. The first orbit will contain, of course, 2 electrons because the first orbit fills with 2. And then the second orbit, what do you have a total of 8 electrons. You have 2 on the first one, which means you're left with 6 on the next orbit. So oxygen is missing 2 electrons to be complete. It is missing exactly 2 electrons to feel complete. Right? So guess who it likes to bond with? It likes to bond with hydrogen. Why? Because hydrogen has 1 electron and is missing 1 electron. So oxygen loves to make bonds with hydrogen. Oxygen's missing 2 and it bonds with a hydrogen and it bonds with another hydrogen. This one has 1 electron additional here, 1 electron additional here, and this one has 2 electrons, right? But what happens is because oxygen is bringing more to this relationship than hydrogen, it's bringing 2 electrons, while hydrogen is only bringing 1. So what happens was when oxygen bonds with hydrogen, the electrons that hydrogen has tend to head towards oxygen. So they're kind of pulled towards the oxygen. So those electrons are kind of pulled towards oxygen. They're not completely pulled away. Oxygen doesn't steal completely the electrons because there's 2 hydrogens, so they don't let oxygen get away with bullying them. So this doesn't make it an ionic bond. Instead, it makes hydrogen have a slightly positive charge. Hydrogen becomes slightly positive because its electron is being pulled. And then the oxygen will end up with a slightly negative charge because it's receiving the electrons closer to it. Okay, it's polar covalent because it forms slightly positive and slightly negative atoms, but without actually forming anions or cations. Okay, so water is a key example of this. What we're looking at here, this drawing of the hydrogen, 2 hydrogens with 1 oxygen, that is water. And water is always bonding, or I should say hydrogen is always bonding with oxygen to form water because oxygen loves to meet with hydrogen. And that's why most of Earth is composed of water. And you can see this here in this diagram. So here's a hydrogen. Here is a hydrogen. You can see the other hydrogen here, right? And then you can see the oxygen right up here. And you can see how the oxygen is bonded with 2 hydrogens forming 1 water molecule, and how then the electrons of the hydrogens pull towards the oxygen, leaving the hydrogen slightly positive and the oxygen slightly negative. Not fully positive and not fully negative. Polar covalent bond. Right? Because of this slightly positive, slightly negative, slightly positive, and slightly negative nature of water, water also forms what are called hydrogen bonds. So what happens is you have a water molecule here with the two hydrogens slightly positive and one oxygen slightly negative. And let's say there's another water molecule over here. Again, oxygen slightly negative. The two hydrogen molecules are slightly positive. But you all know, because you've heard it your entire life, opposites attract. Because the oxygen of one water molecule is slightly negative, and the hydrogen of the other water molecule is slightly positive, hydrogen and oxygen will tend to make a bond here. So what happens is each water molecule is made out of a polar covalent bond, but the oxygen from one water molecule tends to bond with the slightly positive hydrogen from another water molecule, forming what is called a hydrogen bond. And hydrogen bonds are what keep water molecules stuck together, which is why water can form those huge bodies of water like lakes and oceans that it forms due to water sticking to water molecules and tending towards our amazing properties of water. Because of the ability of water molecules to form hydrogen bonds and bond with each other, it allows for water to do so many amazing things. One of the amazing things that water does is it has a high heat capacity. This means that water can absorb a lot of heat. So life on Earth would not exist as it is now. Instead, we would be too hot for life to exist if it wasn't because we have so many bodies of water. Earth itself is made out of 70% water and only 30% land. So that all that water is able to capture most of the heat that enters Earth and therefore keep the Earth at a nice, wonderful, good temperature for us to live in. Our bodies also do this. Every chemical reaction that occurs in our bodies, so every time our muscles contract, we make energy in our bodies, we do digestion, we do absorption, we do breathing, we do walking, we do talking. All of those are done courtesy of chemical reactions, and every chemical reaction produces heat as a byproduct. So our bodies are constantly producing heat, but we're able to stay at that beautiful 98.6 degrees temperature because we have so much water in our body. Our body, much like Earth, is 70% water. So that water helps to absorb a lot of that heat from those chemical reactions that are occurring in our body. Okay, water is also a great solvent, and what that means is that a lot of things are able to dissolve in water. So things like vitamins and minerals and other stuff can dissolve in the water and then be carried via your blood to different parts of the body. It also has great surface tension, which allows things to be able to lie on top of the water. So a good example of that is like your insects that can walk on the top of water. In the case of our body, this matters a lot because fats and oils are able to ride on top of water. One, because of the surface tension, and two, because water has an amazing property called hydrophobic exclusion. So anything that doesn't like water tends to try to want to stay away from water. So your fats and your oils would tend to travel on top of the water. You've seen this if you've ever tried to mix, say, oil and water together or oil and vinegar together, and you see that the oil immediately separates and kind of hangs out on top of the water, and that's because of hydrophobic exclusion. So what happens is in our blood, a lot of things will be carried via lipids, via fats in our blood that can attach things to it, like certain vitamins and minerals, and then carry them through the blood without it mixing with the water and dissolving. So if you want to keep things from dissolving, you carry them in your lipids through the blood and all around the body, which is pretty darn cool. All right, I'm going to stop here before we go too far with this recording, and then we're going to continue by looking at pH and macromolecules in the next